Well, happy Monday. Welcome back to week 5. We're close to the midway point in the quarter already. That seems weird to me.
Yeah,
Feels earlier than that, but here we
yeah,
are.
it feels like the quarter only started yesterday, and yet so much has happened so fast.
Yep, that happens especially in this class. There's so lot to cover, especially if I want to try to get to interviewing at the end, which I would really like to do. Be great.
Interviewing.
Not a topic that's related to algorithms specifically, but as you reach data structures and algorithms, this is the point where a lot of people can start looking for internships. So I want to talk about how to make that process successful. And even if you aren't looking yet, what should you be thinking about? What should you be preparing so that when you are looking, you don't have a mountain of work to catch up on? It should be, you can hop into the process. But we'll cover that as there's time at the end of class, not today, at the end of the quarter. How'd the exam go?
That's horribly the thought was gonna.
It's good. I've had very mixed feedback. I've had some people say this is the worst exam they've ever had for me, and other people say that it's easier than what's been done historically in this class, or was easier than in other classes. So I don't really know how to handle the completely random, it seems like very random feedback from
Very-
person to person.
Am I hearing?
Diverse would be the word I would use.
Yeah.
Am I hearing we need to use randomized algorithm to figure out the feedback?
That would not be a terrible idea. They were probably using that. How'd the exam go? Some random response. All right. Announcements. We have our assignment that was extended due on Wednesday. I'll be getting you the next assignment probably today. We can get through enough material, which I'm pretty sure we will do. So that's going to be the algorithm that we're going to start covering. We introduced it last Tuesday. It's the idea of it, and we'll go through a much more rigorous what it is and why we care. Let's see, I think that is just about everything. Gonna get exams back to you by the end of the week, if that's possible. That's the deadline I've given our grader. And then we'll get started on grading the next assignment as soon as it's in. Any questions or concerns before we dive into new material? Okay, last time we were talking about sequence alignment, which was a very different kind of problem than we've handled in here, or maybe that you've seen in any of your other classes. And this is straight out of an application of computer science for biology. If you're curious, the field of study is bioinformatics. And this is usually the first algorithm you would learn in a class in bioinformatics. And it just so happens to be one of my favorite examples of dynamic programming. And I think that it's very visual, and because of that, it helps to learn the process. So that's why we're doing this rather than anything that is out of the book. It's closest to the string alignment problem in the book, which I think is after rod cutting and matrix multiplication, but it's not quite a string matching problem. It is similar to a string match, an extension of a string matching problem. So we introduced it last time, and we looked at the concept of if we're trying to align two sequences, how many possible alignments were there where at every point we could choose whether to match the existing characters or mismatch the existing characters or place a gap in either of the strings, stretching one of them out a little bit so that we could create future matches by kind of creating a blank or a placeholder in one of the strings that pushes every character we haven't seen further down the line. And if we do that, we see that we end up with the sum from 0 to the minimum of m or n, 2 to the k times m choose k times n choose k, which is an absolute ton of possible alignments. That is exponential with an additional factor on it. So that is disgusting. And if we had to do this for any reasonably large strings, there would be no hope of this algorithm ever finishing in a reasonable amount of time. If we're actually aligning genomes, then that process would not finish in our lifetimes, likely the Earth's lifetime. So let's talk about how do we compute the concept of an edit distance. So we talked about an edit distance last time being a difference between words where we could either permute a character, change a character to another character, or we could insert a character or remove a character as the concept of edit distance. So what is the edit distance from strings perspectives? So let's think about this from a bit of a recursive perspective. If we are partway through this problem and we could look at just the last character of each string. So we have string A broken down into its characters, all m of them, string B broken down into its n characters. We are going to choose one of three things. Either the mth character of string A, the last one, is matched to the nth character of string B, the last one. So the last character is matched to the last character. Or the last character of string A is not matched to a character. It's matched to a gap in string B. Or the character in B, the last character, is matched to a gap in string A. The other possibility for now is that we have some last character in A matched to some character that's not the last character in B, and so basically we have the last character of each mapped to some character before that in either string, but that last one is impossible. Why is that? It violates something that we talked about on Tuesday. We remember what that was?
Very familiar. Sort of a rule about it matching. Let's see. Come on,
Go back, find it.
That.
Was
Oh yeah.
right here. One of them. Yeah, edges are not allowed to cross. And if we are matching this last character in this string to something back here, and this character to something back here, then we find that they cross. And we can't have that. Steel gray.
You gotta be kidding me.
We have a much larger problem here now. We'll figure it out eventually.
Actually, that eraser still worked out pretty well. I know. Still, I am.
All right, so we can't have any crossing of these alignments. That's one visual way to think about these two strings. There's no way that we can have these alignments cross at any point. So if we're matching the last character of both strings to some character before the last character, then it's impossible for them to match. And we can break this down then into a recursive problem. So we can't cross our edges. If we wanted to solve this in polynomial time, this is going to require dynamic programming. But you can imagine now that we're going to break down the alignment of the first m characters in string A and n characters in string B with one of these possibilities for this edit distance. Not this last one, because it's impossible, but any of these prior three, we could possibly say the last characters are matched. One is to a gap, the other is to a gap. For each one of those problems, we can now break down the problem into a new string alignment problem. If we match the nth character and the nth character of A and B respectively, then this is matched, this is matched. This breaks down into a problem of A to the m minus 1, B n minus 1, and we have that subproblem to solve. Does that make sense? If we've said that we are going to match these last two characters, and we know that for sure, that is the best thing that we can do, or an assumption that we're going to make, then we have a new subproblem out of this, matching the first m minus 1 characters of A with the first n minus 1 characters of B, and we could continue making further assumptions. If we don't match m to something from n, then we end up with this subproblem. We're matching m minus 1 characters of A with n characters from B. We break it down into that subproblem. Or if we, and that's if we don't match A sub m. If we don't match A sub n, then we have that problem. So we can break down each alignment into 3 potential subproblems. And we need to find which one of these produces the best result so that we can figure out which one produces this best result. Question?
Yeah, if one of them doesn't match, that means that the other one is matching to a gap.
Yeah. Yeah, so if we have strings that are different lengths, for instance, there are going to have to be some gaps somewhere in there. The question is where to optimize the alignment. If they're of the same length, maybe there are still some gaps. It could possibly be that via some insertion that made strings that were different lengths, and insertion of a strange character that doesn't map well, it makes more sense to gap that than it does to mismatch it, because it will throw future matches into mismatches, and that will have a negative effect on the rest of the alignment. We'll see that in practice when I show some examples, when we go through an example of this. So we can turn these 3 cases into a recurrence. And we're going to call this opt, the optimal alignment between the 2 strings. And I and J tells us the first I characters and the first J characters of A and B, respectively. So if we do opt of the length of A and the length of B, so this would be M and N, then we would have the problem solved. But it's going to be the minimum value of the cost of aligning these plus the value of aligning, this is saying we match the characters that we're on, I and J. So that says that there was suboptimal alignment between all characters that have come so far and all characters that have come so far. And we reach a point that says this next character is going to match to this character. And that would only happen if whatever score we get from aligning the sequences of the characters that are before that, we're going to basically add a match. So basically this is going to be plus a match bonus from here. So we have the score of calculating the I minus 1 and J minus 1 characters, and we add a match bonus for matching. This becomes the cost of aligning those 2 characters. And that can either be a match or a mismatch, depending on whether the characters are the same character or different characters. So really, this should be match or mismatch. Then if we have a gap in one or a gap in the other, then we're creating 2 different subproblems here. We're either looking at, we've aligned from here, and a gap pushes us up, or we've aligned here, and a gap pushes us over. So that's kind of a way to read the table that we are going to construct. But that is the recursive definition. And if we think of this top down, the way that we did for the Fibonacci sequence, we can see that basically we're in a loop that says for every position, we need to look at the optimal ways to align these 3 possible sequences. And those are all going to break down into their respective 3 subproblems. And those are going to break down into their respective 3 subproblems. And we'll see that we have an exponential number of subproblems to solve. But some of those subproblems will overlap, meaning that if we had already solved them once, then we could view the problem as a caching problem. We could look up the solutions. We should only calculate each subproblem once. So instead of thinking of this process top down, we're going to think about this problem bottom up. We're going to start with empty sequences, and we're going to slowly align smaller and smaller, or larger and larger parts of the sequence as we build up to a sequence of length m and a sequence of length n. Each one of those individual cells will rely on prior work that we've already calculated as we do it, so we're naturally caching as we go. This will make a lot more sense with an example. And I think that's where we're headed next. Any questions on these three cases or what they mean?
No.
Just wanna
Yeah.
make sure, so the minimum there, we're trying to find, which of those is gonna give us the minimum cost, right?
Yeah,
And so, because they're all recursive calls, that means that we need to do the entire recursive train for each of them. To figure out which one's the minimum, right?
if we're thinking top down, yes. But we're gonna start from aligning one character to zero characters, and then one character to one character, and then two characters to zero. If we can fill out that table in kind of a diagonal path where we're looking at each diagonal as we go, then we are able to always have the information that we need cached. So they don't break down into subproblems that need to be solved. They break down into subproblems that we've already solved. So all of the work is just taking this minimum of values that we've already calculated. We have a constant time. Is it this, that, or the other for a quadratic number of cells in a table? So we basically have 3 times n squared rather than something that is exponential if that lookup already exists for each of those cells. So we're going to be doing lookups because we've structured it in a way that minimizes the cost. And again, if we broke it down top down, we're looking at a very exponential time solution. So we don't know which of the 3 possibilities is the right one. We're going to need to try all 3 in order to find that minimum, which I will very quickly rephrase as a maximum. So it makes a little bit more sense. So the base case is if you're aligning a 0 character string to a 0 character string, we know what the cost of that is. There's also a base case if we're aligning some amount of one string to a bunch of gaps in the other. That's something that can also be calculated in constant time without any other subproblems. So if I say we have something like this, an alignment of 3 characters to 3 gaps, we would have 3 times the gap penalty as the score for that sub-alignment. And that makes sense. But we can calculate that without any further subproblem work. So here's a visual. This is what we're going to be using to fill in the table. We start anywhere along these, but we're gonna start here and start filling these in where anywhere where we know left, down, and down left are filled, that becomes a cell that we can fill. So we could fill this cell. Once that cell is filled, we could fill this cell or that cell. Once those cells are filled, we could fill that cell, or that cell. And you can see how this moves diagonally up the table. Or you could, on the other hand, start working on just going here, 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 here. So you can fill it out row-wise, diagonally. As long as you have access to those 3 cells, then you can calculate the minimum or soon to be the maximum of those values. It depends on whether it's phrased as a cost, everything is a cost, or something has a net benefit. And a match is going to, from my concern, have a net benefit. Any questions about the table? Where's the answer going to be in the table? Looking at aligning these strings, we're looking at the cost of aligning the entirety of A and B. This would be string A, this would be string B. The answer should be in the top right corner when we're done. Because now at this point, the I is equal to M and the J is equal to N, the lengths of both of those strings. So when we have a score for an alignment of the entirety of both strings, it'll be in that cell.
Closer, yeah, close enough anyway. Yeah, the math checks out. Sorry, I'm just.
But as we go, we need to store where the minimum came from. So if we're currently looking at this cell, and these are our 3 cases, either a match or a mismatch came from this cell, a gap from one string, a gap from this string, a gap from that string. That's how we move from one alignment to the other. whichever one of those turned out to be the best, we need to store an arrow, something that says we came from here. This answer came from there. And that way, when we reach this cell in the same way that we saw with rod cutting, that the answer wasn't given to us. We knew the number, but we didn't know how to break down the rod to receive the maximum profit from that rod. If we just calculate the value here, we'll know the value of the optimal alignment. We won't know how to do the alignment unless we store as we calculate where it came from. When we calculate this very last cell, we're going to look at the backtracking arrows from here back to the beginning. There's going to be a single path as we calculate that, and that path will tell us the optimal alignment that we calculated. So that's kind of it's a two-parter. You calculate the value and then place a back-pointing arrow to where you came from. So yeah, there's our answer. The optimum value for matching n characters to m characters, all of A and all of B. But we need to compute every other cell in this table in order to get there.
Okay.
We can't just target the top right cell, because then we'd be thinking about the problem top down. We would have to say, for every possible arrow that I could draw here, what are its subproblems? Which means from this cell, I also need to look at this. And from this cell, I also need to look at this. And from this cell, I also need to look at this. And you can see just how crowded this is getting as I start to think about this problem top down. And it gets exponentially worse the deeper into this table I get. Yeah.
Is storing the path, that's just for efficiency? Because you could just store just a reference to it and just do a lookup each time, couldn't you?
A reference, yeah. Yeah, the solution really just is a reference to which cell it came from.
Okay.
Yeah, not necessarily anything other than that. That's a good point. I draw it as an arrow because we need to know what the subproblem was, but however you store that subproblem is up to you. You know, a way to be able to retrace it from the end. Because if we start thinking about all the possible paths from the end, now there are 3 arrows out of the end, instead of the eventual 1 arrow that's going to be where the optimum value came from these 3 possible cells. Other questions? All right, so we're storing all of these in a 2D array. You can imagine that this is just a 2D array. There is a bit of non-standard rotation notation. Opt ij, when I call it that, is referring to column I, row j, instead of how you might be used to. This is column major rather than row major. You can, when you implement this, do this completely opposite. You prefer to make a row major based approach. Doesn't really matter, but usually I comes before j when we're making loops. And if you do this, then we're doing it in a way that we're looking at for each column, for each row, rather than for each row, for each column. It just flips where the rows and columns are in the outer loop or the inner loop.
Okay.
And that gives you a row major or a column major ordering for that array. All right, so we're going to fill in any cell for which we know all 3 prior values. And we find that we can calculate that edit distance. I am having you implement this, but I'm giving you a little bit of pseudocode for at least the edit distance portion of this computation. This should make, hopefully, the implementation fairly trivial, but there are always things that come up. So the answer is in the top right cell when we think about it, at least the way that we looked at it. We can use induction to show that every cell contains the best value for any given prefix of string 1 with a prefix of string 2 up to that point. We already talked about the running time, number of entries, m by n, lengths of the 2 strings, and then each entry in the table takes a constant amount of time to fill. Since we're looking up 3 values and comparing and finding the minimum or maximum of 3 values, that takes constant time because 3 is always a consistent number. We're not ever changing the number of comparisons we're making for each cell as we get deeper and deeper into the table. If we did, then this filling in each entry may take more than constant time, and in this case, it's always 3. So running time is m times n, or quadratic. I would think of them as it scales based on both the length and of the 2 different strings independently. So it's best to write that. But if you're asked, well, what order would it run in? This is closer to, this scales quadratically rather than, since the strings could be, in the worst case, equal lengths. And in the best case, one string is a lot longer than the other. It just creates very much like a rectangle versus a square. If you have the same number of characters, you get the most area out of 2 side lengths that are the same, as opposed to one that's very long and one that's very short. So let's talk about finding the actual alignment. We just talked about this, the fact that we don't actually store the path to the solution unless we think about it and store that path as we calculate it. So we need to store the backtracking pointers as we go. And what we actually find when we do this is that we get an alignment that looks something like this, where there are arrows in every other one of these squares as well, but the only ones we care about are the ones out of the last state. So we're going to backtrack with the path. There's always only one arrow out of each one of those squares. And so we can now recreate the path that we found when we looked at the 12th and 9th character respectively. So this would tell us we are matching this A with this A. So this is a match. Then we are gapping this string. So this A is not mapped to anything. So this is a gap on this side. Then we match, then we match, then we gap again, then we gap this way. Match again, gap, match, gap, 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 match. And so this would say the optimal alignment of this, if we were to write out how this is aligned. Let's start with the long one first. We would say, yeah, the A, G, G, T, A, E, G, A, T, C. So the characters that are along the bottom here, that's all that I've written. And then we're going to, I actually am going to need some gaps in this. So, oops. We are mapping this match. So this A maps to this A. This gap says that this A is matched to nothing. So that A matches to a gap. Then we match this A to this G.
Oh, I get it.
So that maps to that. Then we match the C to a G. Then we have another gap as this T is matched to nothing. But then we do the exact opposite. And I'm going to need to redraw this because there's a gap in this string now as we move that gap, and that's matched to this G. So there's a gap matched to a G. Then we match the A and the T. Then we have another gap. This T goes to nothing. Then we match the G and this T. The terrible alignment, by the way. Then we have 3 straight gaps of an A and a T. Then we have 2 gaps in a G and an A. And finally, we match a C and a C. If this is the best possible alignment of these strings, it seems strange, but maybe it is. I haven't gone through the work to verify that or not, but that is basically what the ending alignment would look like. It should end up the same number of characters in the alignment at the end, even if there are some gaps at the beginning or end of some of them. Question?
Looking at this example, it makes me think that if you're doing this for any 2 strings where it's going to be fairly square, you're never going to have it go all the way over and all the way down. So is there some way that we can have it skip the ones at the end just to save
There's no way to know that for sure as we're building the table. And it becomes necessary in order to calculate the maximum of something like up here. We will need to be able to query here, which needs to query here, which needs to query here. So it's extremely unlikely that anything in this corner or this corner are used, but the values are necessary in order to prove that it is the best alignment. And even if we could ignore some proportion, some small proportion of this, it would just be a constant in the running time anyway. But that is a good question and a good note that it's very unlikely that these values are going to be used. Does it make sense how to create an alignment from following this? Exactly what I did to create that? Any questions on that? Okay. At least start an example. We'll see how this goes. Meaning, I don't know if we'll be able to finish in time. So we've basically talked about it all. We've talked about dynamic programming with it. So we want to solve the subproblems in order. We have a polynomial number of subproblems now, which is great, rather than an exponential number of subproblems if we were to tackle this top down. And we can find this natural ordering of subproblems so that the solution to a larger problem breaks down into its smaller subcomponents. For those of you who have some introduction to graphs in other classes, you'll get some here. It's just about the next thing we talk about, but you can visualize this as a graph rather than as a 2D array, and that helps us to think about the ordering of the solution, and also one way we could break this down in terms of nodes of graphs. If this doesn't track for you, don't worry about it. We'll be talking about graphs soon. So let's start building an example. Here is an example, a match bonus. Now we're taking a maximum instead of a minimum, just because I think that is easier to think about. If two characters align when we match them together, we will add one to a score. If we match two characters and they're not the same character, that'll give us -1 to our score. And any gap at any point is -2. So we should build the table. Maybe what I'll do is I'll give people some time. How confident do we feel if I ask people to build up this table? Is that something that's worth doing, or should we? I can at least get you started. Let's do that, and then maybe we can finish it off at the start of next class. So on one side, we're going to leave space for that initial gap penalty. So we have A and G and C and G and A. I'm going to align this with giving space again, A and C and G and A and A. Okay. So the first cell here has score 0. That one. Okay, so the answer is going to be right here in the end. This score is 0 by default. And along both axes, before we handle a single character in any of these, we can add the gap penalty to each of that row and that column. So this is -2, -4, -6, -8, and -10. -2, -4, -6, -8, and -10. Does that make sense why that is? What does this -10 say if we were to try to interpret what the value in that cell means? What does that sub-alignment mean?
nothing else in there, no, no, not right.
Yeah.
I'm not sure.
We're matching A, G, C, G, and A to gap, 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 and gap.
Pretty much.
So each of that entire alignment would have 5 times the gap penalty because there are 5 characters that we've gapped in one string. And since the gap penalty is -2, the entirety of this is now -10. That would be a very silly way to do this. In fact, the worst way to align any string typically is to gap everything in one string and then gap everything in the other. That would leave -20 as the absolute worst possible alignment that we could make. For each of the 10 characters here, they're mapped to a gap.
Yeah,
So we get 10 times the gap penalty. That's the best alignment. We can call it a day, right? So if we're trying to fill in the value of this cell, this A and A, there are 3 places, 3 possibilities of what this could mean. We are now asking, the first one here is we're going to take the A from the second string, map it to a gap here, and then we're going to take the A here and we're going to map it to a gap here. And that would be the process of moving here and then here. This is already broken down as the gap and A, so all we're doing is adding the second calculation there. The first calculation's score of assuming we're mapping this A to a gap to get to this point, I guess this A to a gap to get to that point, looks like that. So we're looking back at the best way to align this A with a gap, which had the score of -2. On the other hand, if we go this way and then up, we would be doing the exact opposite. We'd have A aligned to a gap and gap aligned to an A. And that has the same score, but a different path of how to get there. So this is looking back there, this is looking back there for those 2 possible alignments. Here is saying we're going to match the A with the A. So the only alignment here is an A to an A. So this score is -4, this score is -4, and this score is 1. Because these 2 characters are the same. The A and the A are the same. So we take the match bonus instead of the mismatch penalty. Both of those are possibilities when you look back diagonally, depending on whether the characters match or don't match. So we're going to take the maximum of these 3 values, which is
1.
1, and we're going to put a backtrace arrow in some other color. It shows us how we got there.
I understand. These, let's see. Let's see. Trying to match all these guys.
Any questions on what I did here?
Yeah. I think it makes sense to us. I think.
No questions yet. That's good. We can move on to the next cell.
Which is,
So now we have a choice. We can fill anything that we can move back all the way and see all 3 down, left, or down, left. So either of these cells have a preference. Which one do we want? Doesn't matter too much, but
I don't think it does.
let's go here. I like rows more than columns, like most computer scientists for some reason. So 3 possibilities for looking back. There's here and here and here. So if we're going to fill in this square, we're going to look at, we can either gap from here, and luckily we don't have to worry about thinking about the alignments at this stage. We just see the score here, we can just subtract 2 from it as a way to get here. We can look at this score, subtract 2 as a way to get there. And we can look at this score and figure out, do these characters match, yes or no? Does the A match a G?
No.
No. So we would take this score and subtract 1. So option 1 is 1 minus 2. Option 2 is -4 minus 2. And the other is -2 minus 1.
Yeah.
We want to take the maximum of those 3 values,
Which is -1.
which is -1. So we're going to fill in a -1 is the best way we can do that, and we need to make a backtrace arrow that shows that it came from there. Came from adding a gap to the prior match. Let's spend a few minutes and try to fill out the rest of this row.
Okay.
Feel free to talk to other people, work together, and let's see what we can do with just a. We're gonna do this in a couple of minutes.
Yeah. Yeah, I feel like it should be a lot simpler than we make it look.
What have we found?
Well, let's see, there are like 3 cells and also the gap is increasing by 2 still and. So I think. Not sure if I'm right. I might be wrong.
Okay.
But from that point, I think that the gap for column A to row. Or sorry,
Sure.
column C to row A would be like -3, am I right?
Yep. -3, where does it come from?
So let's see, 3 bottom cells, right? We wouldn't include 1 here, would we?
Yeah, since this A does not match the C,
Yeah,
it has to come from here. We'll talk about what happens when we have ties at the end,
okay,
where we have one. So here, this is just gonna get worse, this is just gonna get worse. This is gonna be the best value here, this is going to be a -5. Coming from here as well.
yeah, that's,
The other options are -7 from a mismatch here, or -10 from a gap there. Neither of those are better than the -5 we have coming from the left. But now, we have a tie. We can get -7 coming from the left, we can get +1 to this -8, because this is a match and not a mismatch now. So that becomes -7, which ties the -7 from the left, or -12 coming from down. But we know the answer is going to be -7. What should we do when there's a tie? Any intuition?
Use the nice looking one.
Yeah, it actually does not matter. When you write this code, you are going to pick whatever one gets the bias. Because you're either picking a match toward the beginning or a match toward the end. If you draw this arrow here, then the match that you're selecting is this first A to first A. You're biasing a match toward the beginning of the string. If you have an arrow that goes down left, then you're saying you're prioritizing the match at the end of the string. And it doesn't matter. So just make sure there is a single arrow here. I'm going to draw that arrow and bias the one at the end.
that,
But again, it does not matter. Neither one is wrong. All right, what do we want to do? We want to try to finish this off with the last few minutes of class. Let's spend a little bit of time working on this, and then I can go over an answer at the start of next class, given that we have something like 5 minutes left.
Yeah, we have 5 minutes exact.
So it would take me about 5 minutes to fill in the rest of this table, but I want people to practice it. So spend some time, work with some people around you, and see if you can come up with what the optimal alignment of these two strings is.
Hmm.
Like a few people don't have paper with them. If you don't have paper, pair up maybe with someone who does.
Yeah. Yeah. Oh, okay, I get it now. Yeah, that makes sense to me. Fascinating. Fascinating.
There were multiple possible solutions.
You,
I drew both arrows where there was a tie, so there are multiple possible equal valued alignments, but I drew one of them in red.
how many alignments did you draw? Dude, serious.
It was a quadratic amount of work. Rather than an exponential amount of work to find that optimal alignment as well as a score for it. So we know the optimal alignment has score 0. And you can trace back any path that works from the top right square down to the bottom left square. And that tells you how to align each one of these in order to get that maximum value.
Okay.
How are we doing with this? Maybe just a quick show of thumbs to feel like, are you on a good track to producing this?
I got plenty more practice to work on. Hold on, I wanna take a picture. No, you're gonna post this on YouTube anyway, but better to keep something close.
Yeah, that's fair. So my challenge to people before tomorrow is if you don't have this finished off, finish this off. Make sure that you understand how we get this, why we get this, and we'll start next class period with another practice problem. Not of this exact algorithm, but another dynamic programming type of problem that will allow us to see the power of dynamic programming.
Actually, to be honest, I'm thinking a lot of this already. Well, I mean, yeah, the only problem is just that. It's like forging a blade in a blacksmith shop. It's a slow
Good analogy.
forge.
Feed it slowly into submission once it's heated up enough to be valuable.
Well, not so that it's about shaping it carefully and sharpening its edge carefully too. So that type of edge, my edge on that is still being sharpened. So. And to be fair, I have a lot of blades of braid lately. And I say that knowing full well, I got myself a dark small themed lightsaber on a saber shop just last night. Oh yeah, just yesterday.
No, I bet.
May 4th sale.
Right?
You never heard Star Wars Day?
Oh, yeah.
Yeah, so